Okay, so welcome to session on symmetric cryptography 2. So there will be 3 talks in this session. And the first presentation is security of truncated permutation without initial value by Lorenzo Grassi and Barton Manning. So please start your presentation.
Hello. Okay. So thanks for the introduction. I'm going to start this presentation with a bit of overview and motivation of this work. So we know that if you apply a truncated permutation on the concatenation of an input value and a fixed initial value, the function that we obtain is indifferentiable from a random function up to a certain bound. So in this paper, we proved that almost the same bound holds if the initial value is replaced by a randomized value. And then we propose some concrete application in the context of parallel variable lambda-adjusted generation. So the organization of this presentation is exactly like this one. So I'm going to start with some preliminary about how to set up a random function from random permutation. Then I show our result of this paper, and finally I propose the concrete application. So first of all, many symmetric crypto primitives are based on public permutation or public function. Just to give some example, the even-months reconstruction is based on a public permutation P. So we take an input X, and the output is defined as the sum of the key plus the permutation applied to the input X plus the key. Or for example, hash function make use of a random function of a public function. For example, the Merkle-Dunbar construction is instantiated by a public compression function f, or the sponge hash function can be instantiated either by a public permutation or a public function. Now we know how to construct a public permutation P with good statistical and or algebraic properties. For example, we can make use of the SPN strategy, and we can choose a good S-box, a good linear layer, and so on. The same is not true for the case of public function. So in this case, what we do is to take a public permutation and to turn a public permutation into a public function. For example, consider the case in which we have two permutations, P0 and P1, that are defined over P bits. We can define the sum of permutation as the sum of the two permutation applied to the input X. And this function is proved to be indifferentiable from a random function up to the B queries. A similar result holds if we have a single public permutation. So in this case, we lose one bit in the domain. So we have the first public permutation is applied on X concatenated with 0 plus the same permutation applied to X concatenated with 1. Now, if we have a single permutation, we can also define other random function. For example, the truncated function. In this case, we have a function that takes in input b minus m bits and return n bits, and is defined in this way. So we take the concatenation of the initial value, the input X, we apply the permutation, and then finally we truncate. So the initial value is of m bits, and the truncation is of n bits. So we take the n leftmost bit of the output of the permutation P. Now, the security of this construction has been studied in the literature. For example, we have a first result by Todis et al. At FSC 2009, and we have a more recent result by Choi et al. At Asiacrypt 2019 that proved that this function is indifferentiable from a random function up to this number of queries. And what is important to keep in mind is that this minimum, we have 3 elements, and this last one is to the power of m, where m is the size of the initial value. So what does it mean? So the initial value is crucial for the indifferentiability. So if m is equal to 0, then we can easily distinguish the truncated permutation from a random function. And the reason is very simple. Okay, if we take this bound, we have to the power of 0, which is 1. So one query is sufficient to distinguish these two cases. And the idea is very simple. So we take y, which is a random element of p bits. We apply the inverse permutation p, and we get x. And then we do our oracle query on x. And if this inequality is not satisfied, then we know that the oracle is the random function with probability 1. So the initial value is crucial, but at the same time is overkill in the sense that there are some hash functions which are instantiated by a truncated permutation with m equal to 0 that are still secure. For example, this is a sponge hash function. So at the beginning here, we have an initial value which is fixed. But in all the other cases, this initial value, so the part that corresponds to the inner part is not fixed. And this function is still secure. So the crucial point is that the attacker doesn't have access to the inner part, can only work with the outer part. So there are some cases where we don't need a fixed initial value. We can have something a bit more, a weaker assumption. So this is exactly the idea that we have in this paper. So the idea is to replace this fixed initial value with a randomized value. So we start from this construction and we replace the initial value with the output of a hash function applied to an input m. And in this case, the hash function takes a message of arbitrary length and return m bits. Now, in the paper, we prove the security of this construction, and we show that if H is a random oracle, if P is a random permutation, then this construction is indifferentiable from a random oracle up to this number of queries. So just to better understand this bound, so if you want k bit of security, we need that m is strictly bigger than 2 times k. So m is the size of the output of the hash function, and b, which is the size of the permutation, must satisfy this inequality. Now, I'm not going into the details of the proof, but the idea is to use the indifferentiable model. So we have a distinguisher, and we have 2 words. One is the word of the randomized truncation function, and the other one is the one of the random oracle. And the distinguisher wants to distinguish between these 2 words. Now, in this word, we also have the hash function and the permutation, because the randomized truncation function is defined via the hash function and the permutation. And obviously, in order to avoid trivial distinction, we need to have simulators of the hash function and of the permutation in the forward and in the inverse direction in this word. Now, the distinguisher can query everything. In this case, the randomized truncation function can query the hash function and the permutation, and in this case, the simulator query the random oracle. So the details are in the paper. As you can imagine, the strategy of the proof is similar to the one proposed by Choi et al. At Asiacrypt 2019, but there are some crucial differences, and if you're interested on them, just have a look at the paper. In particular, the main difference, so if we can have a look to the bound that we can get from the truncation function and the randomized truncation function, the only difference is about this last term. And the reason of this is that in our case, we can have a collision at the output of the hash function. And so that's the reason of this factor 2. Now, possible application is the parallel digest generation. So if you want to set up a hash function, we usually have 2 possible constructions. One is the Merkle-Damker construction, and the other one is the sponge construction. And in both cases, we don't have, so the squeezing part is not done in parallel. So in particular, in the Merkle-Damker construction, we output a fixed size digest by using this process. In the sponge construction, we allow for arbitrary size output, but the output generation is sequential. And in many cases, we prefer to have parallel digest generation because in modern CPU, working in parallel is faster than working sequentially. Now, in the case of PRF, this problem was solved with the Farfalle construction proposed by Bertoni et al. At TOS 2017. And for the case of hash function, we actually already have a solution, and the solution is the mass generation functions. So there are already some MGF construction in the literature. In this paper, we propose a new MGF construction, which is called Cascade MGF, and it is based on this randomized truncation function. So it satisfies the goal to extend any hash function into a parallel extendable out function that generates arbitrary size output. So the definition is very simple. We have a hash function that return m bits in output and a permutation that works over b bits. And the Cascade MGF is simply defined as the randomized truncation function applied to the message and to an index I. So this notation just means that the bit representation of 0 of size L. So this function behaves as a random oracle if the hash function behaves as a fixed output length random oracle. So just to have a concrete example, here we have Cascade MGF instantiated with 3 hash. So we have parallelization in the absorption phase and parallelization in the squeezing phase. The crucial point here is that in the squeezing phase, we don't have any fixed value. So we just have the output of the 3 hash and then the index. Now, to understand the advantages of this construction with respect to other MGF, let me just briefly recall the counter MGF and the change MGF. So for the counter MGF, we need a hash function that returns m bits. And the counter MGF is defined in this way. So we take the message, we concatenate with the index, and then we apply the hash function. And for the case of change MGF, we need a hash function. We need a function that takes an input m plus l bit and return n bits. And here we first apply the hash function to the message. Then we concatenate with the counter, and then finally we apply the function f. So let's compare this construction with the Cascade MGF construction. So first of all, in the case in which f is a truncated permutation. And the advantage, as you are going to see, is about the size of the index L. So here we have K is the security level, P is the public permutation, and the output of the hash function is a piece of 2K bits. So in the case of Cascade MGF, we have that the counter can be is of size P minus 2K bits, because basically P is applied on B bits, and the size of this element is of 2K bits. In the case of change MGF, the size of L is P minus 3K minus 3K bits. And the reason is that we have a counter, we have the hash function, but we also have this initial value of K bits. So what does it mean in practice? This is very important in the case in which we have permutation that works over small fields. For example, we have Gimli or Xudo that work over 384 bits. And assume that we want 128 bits of security, then in the case of change MGF, the size of the index L is just 0 bit. So we can just have one digest block. In the case of Cascade MGF, the size of L is 120 bits, which means we can generate up to the power of 128 digest blocks. So the difference is huge. So another possibility is to instantiate this function f with the sum of two permutations, P0 and P1. And in this case, L, so that the size of the index, the size of the index I is P minus 2K, because we don't have an initial value, and we can output P bits. So here the advantage comes from the number of permutation code that we need to generate a certain amount of bits. So in the case of Cascade MGF, we can generate B minus K bits with one permutation code. In the case of chain MGF, we can generate P bits, but we need two permutation codes. And this inequality is always satisfied if P is greater than 2 times K, but this condition is necessary because otherwise we can get a collision on the hash function faster than the security level. So the comparison between Cascade MGF and counter MGF can be found in the paper. And with this one, I am going to conclude. So in this paper, we proved that a truncated permutation instantiated by a randomized value is still indifferentiable from a random function. We propose a new MGF construction, which is called Cascade MGF construction. And we show that this construction has concrete practical advantages with respect to other MGF construction proposed in the literature. Thank you very much for your attention.
you very much. So, any question or comment? Okay, so I have one question. So, is it possible to prove the security or outrank from the weaker notion of hash function like preimage aware? Yes. So your assumption for hash function is random walk.
Yeah.
Right? So is it possible to meet the security assumption?
So for sure, we need the collision resistance. About the preimage, I'm not sure. I have to check, honestly.
Okay.
Do you have any idea to make the construction, truncation construction to be more secure than beyond the initial value bit? So your construction also stuck with the collision probability m over 2. So maybe there any idea to make it better?
Not really, because I mean, if you have a collision on the hash, the construction is already broken. So no, at the moment, I have no idea, to be honest.
Okay, thank you.
Thank you.
Any other question? No question from the room on Zoom? Okay, so yes, sound speak again. Okay, so the next presentation is the multi-user security of the sum of random permutation by one secretary, Egan King, Joan Lee, and Yeonmin Lee. So one sec, please start.
Thank you for introduction, and let me start my presentation. My topic is multi-user security of the sum of truncated random permutations. So like this. Okay, thank you. My name is Won-seok, and my co-authors are Hee-kyum, Ju-young, and Young-min. And let me start. So this is our outline for today, and let's start with introduction first. Block ciphers are one of the most common primitives in the world, and for example, AES is commonly used in many ways, such as wireless security, processor security, file encryption, SSL, TLS, and more. So block cipher takes n-bit input and output n-bit strings. So if you want to encrypt more than n-bit data, you need repeatedly apply this cipher again and again. However, naive construction based on a block cipher such as MAX or AEAD may guarantee the birthday bound security. For example, counter mode is commonly used in encryption schemes, but only guarantee the birthday bound security. And there is a simple solution to replace the block cipher with pseudo-random functions, and this problem may called Ruby-Legov-Vegard problem. There are two natural ways to building PRFs from block cipher, and TRP and SOP, where TRP means truncation construction and SOP means XOR of two independent permutations. The security of TRP was proven by Gilboa et al. And they proved the tight security in the Journal of Cryptology in 2018. They also showed that this tight result actually follows from a result of Stam's paper in 1978. And recently, Gunxing and Manick introduced a new construction, summation truncation hybrid construction. And this construction is made by concatenating outputs of two independent TRPs and some of discarded bits from those TRPs. Surprisingly, those reusing bits does not degrade the security of STH, and therefore STH has same security level with TRPs. On the other hand, the security of SOP has a long history, and notably, Katalin showed the security of SOP with mirror theory. However, the mirror theory was not verifiable, and Dai et al. Showed its security again with different approach via chi-squared method. And very recently, Bhattacharya and Nandi showed that sum of 3 permutations can be secure up to 2 to the n queries for each of 2 to the n users. Now let's talk about security definitions. So our cryptographic systems are composed of secure cryptographic primitives and supported by secure proof. So in our case, the cryptographic system will be PRF, and this will be made with block ciphers. And the keyed block cipher can be regarded as a secure keyed random permutation, and secure keyed permutation is not be able to distinguish from a truly random permutation. Using this model, how to show the security of given construction? We will set the indistinguishability gain, where given two crypto system, namely ideal world and real world. For our case, ideal world will be a truly random function, and real world will be a PRF algorithm we propose. Here, an adversary distinguisher interacts with an oracle in a black box manner, so it only knows its queries and answer pair. In our case, we will consider multi-user security. So there are mu number of users. Each user have independent keys, and for ideal world, they also have independent random functions. So now let's talk about our research. And this is the construction we propose, SAT1 and SAT2. They are kind of the sum of truncated random permutations. And SAT1 is built upon from single permutation with the domain separation, and SAT2 uses independent 2 random permutations. We also studied about the sum of 3 random permutations. It doesn't work. Okay, so SOP 3.1 is indeed Bhattacharya and Nandi studied in the last Asiacrypt, but they did not study about SOP 3.2. SOP 3.2 is a variant of SOP 3.1 using different permutations. And this is our research, where the security implies the upper bound of distinguishing advantage of each construction. Mu is the number of users, and Qmax is the maximum number of queries per users. M is the output bit, and rate is the output bit per permutation call. As you can see, SAT1 and SAT2 are secure up to 2 to the n queries per each user when mu is smaller than 2 to to the n minus m users, which is same security level with SOP3. And if the number of users is more than that, SAT2 can be more secure than SAT1. Similarly, SOP32 can be more secure than SOP31 when number of users are huge. To ease our understanding, let me explain about the multi-user security of the sum of two random permutations. If we use naive approach with previous result, we can multiply number of users mu for the previous single user bound and obtain this bound. For this case, when we let mu be 2 to the n, then Qmax should be smaller than birthday bound. However, using our research, by obtaining our new bound by letting m is it is a typo. We should letting m equal to n. So when we letting m equal to n for SAT2, we will obtain this bound, and it means that when mu is equal to 2 to the n, Qmax can beyond birthday bound, and the following is also typo, and m is when smaller than n cases. This is the first bound because no one ever considered the security of sum of truncated random permutations. For technical contribution, we used proof technique based on chi-squared method. And for chi-squared method, we should compute the expectation of the chi-squared divergence for sum of truncated values. And it was not easy and almost impossible when your first attempt. So we need to modifying the domain over the expectation is taken. So, and we also need to using inverse counting, because if you loosely counting some numbers, then it immediately makes the whole bound looser. For applications, SAT1 and SAT2 can replace the key generation algorithms in AES, GCM, SIV, or CWC plus, or SCM. Those constructions are using synthetic IVs derived from secure PRFs, and SAT1 and SAT2 can replace those secure PRFs. So either be more secure in the multi-user setting. Now I will tell you about our security proof. Let's start with defining distinction game. That the ideal world will be a real random function, and the real world will be summation and truncation construction. In this case, we will consider about SAT2, and by defining the probability description, we can express the advantage upper bound like this. To ease our understanding, we will also define the new experiment which choose their output independently from given input. I want to note that this setting is not necessary, but it is only for ease our understanding. So the statistical distance will be the same. And finally, we want to give some extra outputs, namely R, during the game. And R in the real world is the value of truncated output of P1. On the other hand, in the ideal world, there is no P1, so R should mimic that of in the real world. So it's the additional information, so we can upper bound the statistical distance like this, and the advantage will be same. To upper bound the statistical distance, we will use chi-squared method. By defining the probability of the ith answer obtaining by adversary interacting with each word like this, and the chi-square method make us to able to bound the statistical distance like this, where the chi-square divergence defined like this. So we need to calculate the probability of the ith answer. How to do this? Let the ith answer be R and Y, then we will define the two random variable. SI or RY is the number of possible output pairs from P1 and P2 consist with the previous answers. And TIY is the number of possible output pair from P1 and P2 for any X. Then the probability of obtaining the ith answer in the ideal world and real world will be like this. As you can see, SI, RY will be cancelled out, and we will only consider TIY. So how to compute the expectation of TIY and the variance of TIY, since we also compute the scale of TIY and it can be expressed by the variance. We solve this problem by defining a larger domain, namely H, with consistent with Z. So H contains I-L outputs of P1 and P2 before truncating. And we successfully showed that the expectation will have same value even if the domain is changed. And finally, we can show the following lemma. And from this lemma, we can evaluate the expectation of chi-square divergence. So let me conclude my presentation. And this is the open problem. So because there was some construction using truncated bits efficiently, I think our construction also can use this idea. And secondly, application of AEAD is surely will be a good open problem. And finally, generalization of this method to obtaining better multi-user security bounds for various construction will be also interesting work. And I'm actually ongoing to work to do that. So this is the end of presentation. Thank you for listening. And any questions?
Thank you very much. Any question or comment?
Hi, just a quick question. In one slide, you say when U is to the end and it's secure up to birthday bonds or query to the end of the two.
This slide, right?
Yeah. What does that mean to have more users than queries?
Can you ask?
What does that mean concretely for the adversary that you have more users than queries? That means there are users that you want to queries to, or does that help the adversary adjust?
So mu is the number of users, and Q max implies the queries for each user. So
okay, so effectively the adversary does Q times U query.
Yeah, that's it.
Okay, thank you.
Any other question? Question? No? Okay, let's speak again.
Thank you.
So the next presentation is functionable key wrapping and its application by Matilda Backender, Felix Gunder, and Kenny Peterson. So Matilda, please give your talk.
Thank you. Thank you for the introduction. Yes, so my name is Matilda, and this talk is about punctuable key wrapping and its applications. And this is joint work with Felix Günther and Kenny Patterson from the Applied Cryptography Group at ETH Zurich. So in this talk, I will try to tell you what punctuable key wrapping is, how it can be used, and why we think it's interesting. So starting with the what, let's forget about puncturing for a moment and focus on key wrapping. You can think of key wrapping as being authenticated symmetric encryption, where the plain texts are cryptographic keys. And this can be used to protect keys in storage and during transport. It can also be used to build so-called key hierarchies, which are systems where one key is used to protect multiple other keys. And this is useful, for example, in applications that have a lot of keys to ease key management. So to take a concrete example, let's look at file encryption. So imagine that you have a bunch of files which you would like to outsource to some untrusted storage. And since the storage is untrusted, you probably want to encrypt your files first. Now to do this and still adhere to best practices of key separation, you probably want to generate a unique data encryption key per file to encrypt each file separately. However, you're now stuck with a bit of a key management overhead because you have to store all of the data encryption keys in some protected storage. So to get around this, you can generate what's known as a key encryption key, or a KEK, and use this to wrap or essentially encrypt all of the data encryption keys. And now you can outsource also the storage of the wrapped data encryption keys to the untrusted storage. And in this setting, the wrapped data encryption keys are usually stored together with the encrypted files. So if you want to delete some files, you would also delete the corresponding data encryption keys. And this is one example of a key hierarchy. You can also have key hierarchies with multiple levels, where keys above the key encryption key level are used to protect the key encryption keys, etc. And key hierarchies are ubiquitous in practice. So for example, this figure is taken from Google Cloud's white paper, where they show their encryption key hierarchy. And it's slightly rotated compared to the illustration that I just showed you. So you twist your head like this 90 degrees, you might see the similarities. We have the KEK on the right, the wrapped data encryption keys on the left, and the encrypted files or data chunks in the middle. So let's take an example of a key hierarchy in a slightly different setting, namely TLS session resumption. Here, the scenario is that a bunch of clients have shared a session with a server in the past, during which they exchanged so-called pre-shared keys, or PSKs. And the pre-shared keys are symmetric keys, which can be used to bootstrap the security of resumed sessions in the future. And the issue here is the same as in the case of file encryption, namely key management. Because it might be the case that the server serves potentially millions of clients, and it could be infeasible for it to store all of the pre-shared keys. So to get around this, TLS allows the server to use its long-term key to encrypt the pre-shared keys and outsource the storage of them to the clients in what's known as session tickets. And when a client wants to resume a session, it simply sends the session ticket back to the server, which uses this long-term key to decrypt the pre-shared key and start the session. So now we've seen two examples of key hierarchies. Let's have a look at what happens in the case that the main key is compromised. So starting with the case of file encryption, if the key encryption key gets compromised, then all of the wrapped DEX and hence also the files are decryptable. And perhaps somewhat surprisingly, this also includes the previously deleted files, because as you'll recall, these were placed in unprotected storage. So it could be the case that some adversary had access to the storage and took a snapshot of the ciphertexts before the files were deleted. And this violates the forward security of these deleted files. So we cannot hope to protect the confidentiality of the files which are still in the storage when the key is compromised. But we should provide security for the previously deleted files. And one way of achieving this is to perform periodic key rotation. Key rotation is an operation in which you sample a new key encryption key and replace the previous one, and you use the new key to rewrap only the data encryption keys corresponding to the non-deleted files. Now, if the new key encryption key is compromised, then the deleted files for which the data encryption keys were not rewrapped remain secure. However, this comes with a drawback of the rewrapping or re-encryption overhead, because you have to rewrap all of the data encryption keys that correspond to the non-deleted files. Hence, you probably don't want to perform key rotation after every file deletion, but only at some fixed time interval. So for example, in the case of Google, their standard key rotation time means that you only get forward security after about 5 years. So key rotation provides a form of coarse-grained and delayed forward security. Moving over to the setting of TLS, if the long-term key of the server is compromised, then the pre-shared keys of all the past sessions, including completed sessions, are compromised. And this is because the client sends the session ticket back to the server in the clear, so an eavesdropper on the network could store the session ticket and then use the compromised long-term key to decrypt the pre-shared key. And again, this violates forward security, which is an outspoken goal of TLS. And in this setting, key rotation is unfortunately not a possible solution. Can you think of why? So the reason is that the server has no way of fetching the session tickets from the clients in order to re-encrypt the pre-shared keys. But luckily, at Asiacrypt in 2019, Aviram, Gelet, and Jäger proposed a solution. They designed a forward secure session resumption protocol for TLS using what's known as puncturing. And puncturing is an operation which updates the key in such a way that it can no longer be used to decrypt specific ciphertexts. In the case of TLS, this would be used to puncture the long-term key of the server on the tickets of completed sessions to get forward security for the pre-shared keys. So this is great. We have a way of getting forward security without key rotation. However, the solution is specific to the setting of TLS, and it doesn't carry over, for example, to the case of file encryption, where we would ideally like to have the same security guarantees. So what can we do about that? Well, if we zoom out enough, we can see that these settings have a lot in common. Namely, they both have a symmetric key hierarchy. They would both benefit from forward security, and key rotation is not ideal in either case. And there are other applications which also fit this description. So wouldn't it be nice if we could find a solution that works for all of them? This question led us to look again at these common properties. And in particular, we noted that you can build key hierarchies using key wrapping, as in the case of file encryption, and that you can get forward security from puncturing, as in the case of TLS. So we asked ourselves, what happens if you combine puncturing with key wrapping? And perhaps not surprisingly, this led us to introduce functionable key wrapping, which is a new cryptographic primitive, which provides an abstraction layer between these high-level applications and the lower-level primitives, such as puncturing and encryption, which we build it from. And it gives us exactly what we want, namely fine-grained forward security without the need for rewrapping or key rotation. And it's generic, meaning it can be used anywhere where key wrapping is currently used. And it's also generic in the way that we instantiate it from its building blocks, as you'll see in a moment. But first, let's take a look at the syntax and security of punctuable key wrapping. So starting with the syntax of normal key wrapping, we have a wrapping algorithm, which takes as input the wrapping key. And this would be the key encryption key in the case of file encryption, or the server's long-term key in the case of TLS. It also takes as input this black key, which is the data key to be wrapped, and some header with context information, such as the permitted usage of the key or the expiration date. And it outputs the ciphertext, which authenticates the header. And unwrapping simply undoes this, so it takes as input the header and the ciphertext, and it outputs the unwrapped key. Now, to enable puncturing, we add an additional input, which we call a puncturing tag. And you can think of this as being a unique identifier of the ciphertext. And the puncturing tag is also the input to the puncturing algorithm, which acts on the wrapping key and outputs a punctured wrapping key, which you can think of as a wrapping key that just had a hole punched in it at the point of this puncturing tag. Because now if you try to unwrap a ciphertext with this puncturing tag that the wrapping key was punctured on, then unwrapping will fail. And puncturing is an operation that you can perform iteratively on the wrapping key. So you can take the punctured key and input it again to the puncturing algorithm to puncture it on a new tag and so on. And for correctness, we want that unwrapping still works on any puncturing tag that the wrapping key was not punctured on, but that it fails for those that it was punctured on. So the latter already goes in the direction of security. And a little bit more formally, what we want in terms of security of a puncturable key wrapping scheme is first and foremost the sort of basic security of key wrapping, namely confidentiality of the ciphertext in the sense that ciphertexts are indistinguishable from random bits. Integrity of ciphertext in the sense that if you try to unwrap on a forged ciphertext, then unwrapping will fail. And forward security, which is exactly this property that unwrapping using a puncture tag on the ciphertext with that puncture tag will fail. Now, it turns out that the applications that we're interested in need slightly different flavors of these security notions or combinations thereof. So in our paper, we explore various levels of security for puncturable key wrapping schemes and also relate them. So moving on to an example of how you can build puncturable key wrapping. And this instantiation follows the approach of Aviram, Gellert, and Jager and generalizes it. So starting with the wrapping algorithm, if we zoom in, then inside we have a pseudo-random function, which I hope you're all familiar with. And it takes as input the wrapping key as the PRF key and the puncturing tag as the PRF label. And we treat the output as the key for an AAD scheme, to which we input the context information as the additional data and the key to be wrapped as the message. And we use the ciphertext as the wrapped key. And unwrapping starts the same way, namely it evaluates the PRF on the puncturing tag to get the AAD key, and then uses the key to decrypt the ciphertext and outputs the unwrapped key. But how do we get puncturing from this? Well, we don't actually use any kind of pseudorandom function, but a special type known as a puncturable pseudorandom function, or a PPRF. And a PPRF has exactly what we need, namely a puncturing algorithm, which on input the PRF key and the label outputs a punctured PPRF key, which can no longer be used to evaluate this label. So again, now if we try to use this punctured PPRF key in the unwrapping algorithm to evaluate the punctured tag, the evaluation will fail and we won't get the AAD key, which we need to decrypt. So unwrapping will also fail. Hence, the result of this instantiation, well, it's an efficient construction because we know how to build AAD schemes efficiently, and puncturable pseudorandom functions can also be built efficiently, for example, using the Goldreich-Mikali tree construction. And it inherits the basic security properties such as confidentiality and integrity directly from the AAD scheme, and forward security from the puncturable pseudorandom function. So with this, let's go back to an application and have a look at how we can use puncturable key wrapping in the setting of cloud storage to get fine-grained forward security for deleted files. As a reminder, here's the syntax for puncturable key wrapping schemes. So the setting is that we have a user which has a wrapping key and a bunch of files which it would like to outsource to the cloud. And for each file, it generates a data encryption key, uses this to encrypt the file, then samples a puncturing tag and uses this to wrap up the data encryption keys. And now it can outsource all of this to the cloud. And we're interested in the security of deleted files. So if the user sends the request to the cloud that it would like to delete file 1, well, the cloud might respond that the file is deleted. But since the cloud is not trusted, we don't actually have any guarantees that this happened. So, concretely, the cloud might be malicious and just ignore the request to delete the file. Or even if the cloud is honest, it might have been compromised by some external adversary that took a snapshot of the ciphertext. It could also be the case that the file is not properly deleted because of backups or disaster recovery. This is actually often the case in practice, or that just, it was kept around because of faulty processes. So this is not great. Like, we have the same problem as before. If the user's wrapping key is compromised, then all of the files, including the deleted one, are potentially vulnerable. And this is not what we wanted, right? So that's where functional key wrapping comes to the rescue. If the user wants to be sure that they have forward security of the deleted files, they would generate the tag corresponding to the file that they want to delete, and then use the puncturing algorithm of the punctuable key wrapping scheme to update the wrapping key. And crucially, replace the old copy of the wrapping key with this punctured version. Because the new punctured version can no longer be used to unwrap the data encryption key that was used to encrypt the file that you want to delete. So if the punctured wrapping key is compromised, then we have confidentiality of the deleted file. So in conclusion, we get fine-grained forward security without the need for key rotation or rewrapping. And there's nothing specific about this example of cloud storage. Functional key wrapping can be used in any place where key wrapping or key encryption is currently being used. So with that, let's wrap up. I presented to you punctuable key wrapping, which is a new cryptographic primitive that provides an abstraction layer between these high-level applications and primitives such as puncturing and encryption. It enables fine-grained forward security and can be integrated into all applications that have a key hierarchy or use key wrapping. And if you're interested to learn more, in the paper, we also explore various security notions for punctuable pseudorandom functions and their relations. As I said earlier, we explore security notions for punctuable key wrapping schemes and relate them. We also provide an integration into TLS, where we recapture the work of Aviram, Gelet, and Jager and improve upon it. And we formalize all of the above in security games and give proofs and bounds. Thank you for listening. Oh, sorry, yeah, our full version is on ePrint. Here's the link. With that, I want to say thank you for listening and feel free to get in touch.
Thank you very much. There are any questions or comments?
Thanks for the great talk. How does the key size of the punctured key grow in the number of deletions you do? I would assume you kind of carefully choose the tag so that deletions are efficient or something like this.
This is a really great question. And of course, it depends on how you instantiate the punctuable key wrapping scheme. But if you use the GGM construction for the PPRF, then yeah, you have a potentially logarithmic growth in the size of the key if you choose random tags, but you can choose them sort of in order to get better bounds on the size. However, at least in our treatment, we let the application decide on this because you can get better privacy if you choose random tags than if you let it be in order. So I would say that the application, maybe like the security is probably more important than the size of the key, or perhaps the application decides which is more important. But yeah, that's sort of the generic answer is that it depends on the application and on the instantiation. You can also think of instantiating a puncturable pseudorandom function, for example, using a Bloom filter, in which case the size of the key actually decreases as you puncture, because I mean, essentially you just throw away keys to puncture, but then you start with a large secret key to begin with instead.
Any other questions? Questions from Zoom? No? Okay, so let's thank speaker again. Okay, so all talks finished. Thank you very much.